One of the major problems with parallax is that it can only work for so far. As after you get to a certain point, it's really, really difficult to get an accurate angle, and you end up, not being able to measure any distances above a certain level. Typically, with spectroscopic parallax, that's good up to about 100 parsec. Okay, and this image here can show you, difficulties with determining that angle. So we need some other methods, all right? But let's begin talking about the rating systems that we've used historically, actually, and get into the math about that for the brightness of stars as they appear in the sky. So we have a couple different terms here that we want to go over: apparent and absolute magnitude. And the first we're going to talk about is apparent magnitude. It is a rating system for how bright the stars seem where they currently are from Earth. So I'll write this up here. Okay. Rating system for how bright. Now the idea here is that the ancient Greeks actually ordered the stars in terms of their brightness based on a scale from 1 to 6. And what they said is that 1s were the brightest in the sky and 6s were the dimmest in the sky. And we actually ended up keeping that system in use today, a little bit, okay? But we ended up applying a bit more math to it. So the ancient Greek system, like I said, okay, 1 through 6, 1 was the brightest, 6 was the dimmest, all right? And so what the modern magnitude system has done is that we've kept this, and what we've said is that on a scale of brightness, okay, what we're going to say is we'll keep these numbers 1 through 6, but we'll make it a little bit bigger. We'll keep going on either end. And the main idea here is that a difference of 5 on the scale will indicate a change of brightness of 100, of a factor of 100, okay? So a factor of brightness of 100, okay? So if you have a change, go up by 5, it's going to be dimmer by 100 times. If you go, down by 5, it's going to be brighter by a factor of 100 times. So exactly how do we mean that? Well, let's look at the equation here that we can put in here, but what we'll say is that the ratio of brightnesses, okay, this is our factor right here, all right, it's going to be equal to 100, so the negative m all over 5, m being the apparent brightness, apparent magnitude, excuse me, okay? And what this tells us, okay, is if, we have a star of apparent brightness B, okay, we'll assign it a magnitude of m based on some reference value, okay? So what we do is we have assigned a reference value where m is equal to 0, okay? And saying that the brightness of a star where m is equal to 0 will be given as this. According to the ancient Greek system, this works out quite well. Okay, this is the number that we can approximate 0 on that scale to be. All right? So this ratio right here shows us, okay, how this is going to go up. So in other words, okay, the big idea, the math behind this. So, quick look at the math here. The idea that I'm trying to get at is that the ratio of these brightnesses, all right, think of it this way. 0 is the baseline, 0 minus m, all right, all over 5, all right, is effectively what we're doing. It's the difference from 0, okay? So if we're going below 0, okay, we're going to have an increase all right, that's going to end up making this positive, okay, in the brightness. And that goes along with what the ancient Greek system did, which was becoming brighter as it became more positive. Brighter as it became more negative in the scale, okay, closer to 1. And we go to 0 just as a baseline for the modern system, okay, which is where this equation comes from. So if we continue with the derivation that I was making here on this slide, these are, this is the baseline set of numbers, all right? Let's just do a little bit of math with this. If we take the log of both sides, all right, so it looks like the following. We end up, all right, with this, all right, log of b over b naught, and this is going to be equal to, all right, really quickly here, negative m divided by 5, okay, times 2, since it's log 100, it's base 10 right there. All right, and if we rearrange this equation, we end up getting m, okay, the apparent magnitude that we can calculate based on the brightness that we measure, according to that scale that we'd set up, is equal to negative 5/2 times log of b all over b naught. Okay? So another thing to point out is that this equation that we have above, we can shorten this as well to the following, to 2.512 to the negative m. That's just 100 to the 1/5 power, if you want to have that in there as well. Okay, so either of these could work. Yeah, both are acceptable. Oops. And that's just the b all over b naught. So there we go. So 2 different versions of that equation right there. So this is if you want to solve for the brightness and you have the apparent magnitude. This is if you want to solve for the apparent magnitude and you have brightness. Okay. So let's compare some actual stars here. All right. The apparent magnitude. All right. So here we have stars in Orion with apparent magnitudes of 0.3 and 0.9. Betelgeuse and Rigel. I'm never sure how to say that one. Some of these words are awkward. But some of the brightest stars in the night sky. So here we go. Sirius is the brightest star in the night sky with a apparent magnitude of negative 1.5. Venus, when it's at its brightest in the sky, is negative 4.4. The Sun, negative 26.8, the brightest object obviously in the sky. Okay. The faintest stars that you can see are 6 or 7, as the Greeks identified them, and the faintest stars we can see with telescopes from Earth are about positive 25. So let's do an example here. We want to solve for the apparent brightness of Sirius A based on the little table there. So the apparent magnitude, all right, is going to be equal to negative 1.5. If we pop that into the equation here and rearrange it a little bit, b all over b naught, all right, is equal to 2.512 to the negative m. So we solve for b, it's just going to be b naught times 2.512 to the negative, whoops, to negative m. And substituting our values in here, our reference brightness or intensity. So negative 1.5, all right? And this is going to work out to 1.00 times 10 to the negative 7 watts per meter squared. All right, so that's just if you went to a table and you want to figure out the apparent brightness based on the apparent magnitude, you could do that. So that's a common calculation that you would probably have to do in astronomy. So there's this new idea, there's another idea here called absolute magnitude. And as always, I like to imagine disembodied hands messing with the universe. And we can imagine our disembodied hand taking a star, and if we placed it, okay, that star 10 parsec away from the Earth, and measured its apparent brightness, all right, or got its apparent magnitude, got its apparent brightness, and then calculated its apparent magnitude from that, that would be what we call the absolute magnitude. So I'll repeat this here. The absolute magnitude a star would have if placed 10 parsec from the Earth. All right. So how do we calculate absolute magnitude? Well, if we consider two different stars, all right, which in this case will be the same star from two different distances, but we're just going to consider it as two different stars, all right? Instead of the equations that we had from before for apparent magnitude, it looks something like this. Oops. Negative m1, okay? And the other one will look something like this. All right? And then, let's see here. From here, all right, what we can do is we can set up a ratio of these two, and it's going to end up being with B naught, all right? And when we bring the two of these together, our equation would be B1 over B2 equal to 2.512 of M2 minus M1. Whoops, I forgot a negative sign up there. There we go. All right, so what we can do here, okay, is say that we have, all right, our say that B2 is what we call the brightness for the absolute magnitude, right? And M is going to be B2, we'll call it big M, all right? And that's going to be the absolute magnitude at 10 parsec, all right? So in other words, B is equal to L over 4 pi times D squared, and big B is equal to L all over 4 pi at 10 parsec squared. All right, and what we have here, we'll just replace those values. B all over, little b over big B, 2.512. All right, big M minus a little m. Okay, so we're going to extend the page here. I'm just going to call M1 little m, okay, for now. If we substitute for little b and big B, all right, so we have our L over 4 pi D squared over L over 4 pi times 10 parsec squared. L, we're going to cancel out sort of 4 pi's. And we end up with this thing. Actually, you know what? I'm just going to erase this and then write this other one in first. We're going to end up with D all over 10 parsec. This whole thing to the negative 2, all right, is equal to this. All right, so if we take the log of both sides here, negative 2 log D all over 10, all right, is equal to big M minus little m log of 2.512. And we do a little bit more arranging here, okay? What we can end up with, a log of 2.512, since before, actually, we had shown that this is base 10, all right? We know that this is the 2/5 power, since it's 1/5 from 100, and 100 is 10 to the second. So what I mean is we can rewrite this as the following. All right, and a little bit more fun math here is going to yield the following. Okay, and this is our equation that's going to end up relating distance, apparent magnitude, and absolute magnitude. So if you know apparent magnitude and the distance to the star in parsec, make a mark here, D is in parsec, okay, then you can calculate what we'll call the absolute magnitude, which is kind of a way to put all the stars in a level playing field when comparing them, okay? So you have apparent magnitude, which is going to be looking at how bright the star is when, whatever its position is in the Earth and putting it on that ranking system, and then absolute magnitude, putting it at a distance 10 parsec away, and then ranking all the stars according to their brightness. All right? So that's it for this video. The next video is going to be some examples with apparent and absolute magnitude.